It's my pleasure to introduce Xiaowei Jia, who is an assistant professor in the Department of Computer Science at the University of Pittsburgh. But he's been with this project for a long time, because before that he was actually at the University of Minnesota and was one of the starting members of this. So with that, Xiaowei, please take it away.
Yeah, it said I cannot start screen sharing. Okay, yeah, now I should be able to. Can you see my screen? All right. So, hello everyone. This is Xiaowei Jia from the University of Pittsburgh, and my talk today is going to be on this physics-guided machine learning for model initialization using physical simulations. So first, I want to give some context about these two types of models that have been very widely used in many scientific problems. The first one is called physics-based models, or sometimes they are called like mechanism models or process-based models. And these types of models have been built mostly based on our current understanding of many scientific theories. And at the same time, actually, they also use a lot of like simplified representation, like approximations or some parameterization processes, either because some processes are just not fully understood by people, or they're just too complex to be directly modeled. So that's why these physics-based models, their predictions are not always accurate. And also another limitation of this model is that they always make some simplified assumptions. For example, many models assume some physical parameters are static over either space or time. And on the other hand, machine learning models these years have found a lot of success, especially people have found that these machine learning models usually can outperform existing physics-based models if we are provided with sufficient training data. But in practice, in many scientific problems, it's going to be very costly, very expensive to collect a large amount of training samples. And also many physical processes, they are very complex. So they involve a large number of physical variables, and this relationship between these variables can change over space and over time. So it's very hard for machine learning models to automatically extract this complex relationship from data if we are only provided with limited training samples. And another issue about machine learning model is that they're mostly focused on mining the statistical relationship from data. But these learned patterns from this available training set may not be able to generalize to scenarios that look very different from our training samples. So given this, the power and the limitations of these two types of models, so in recent years, there's a growing interest of building such a physics-guided or such a hybrid physics and machine learning models. So in our recent survey paper, we have summarized several different approaches for integrating physics into machine learning. And here we list a few of these very popular methods. So first, one can build a new loss functions to penalize those predictions or some intermediate variables in machine learning model that significantly violate these established physical laws. And the second approach is that we can build new model architecture or some neural network architecture to embed these known physical relationships amongst different physical variables. And the third approach, which is the focus of our talk today, is to transfer some physics to inform the initialization of these machine learning models. So for example, in previous studies, people have used this simulation data produced by some physical models to pre-train the machine learning model. So the idea is that if we can pre-train the machine learning model using a large amount of simulation data, then it's very likely that this machine learning model can get much closer to its target solution. Then it only requires very fewer amount of training samples to fine-tune itself to the target solution. But there are still several limitations of these pre-training or this initialization method. So first limitation is that most of these methods, they require some high-quality simulations. So, but this is often not available in many scientific problems because of this uncertainty in selecting these model parameters. So here we give an example for lake temperature modeling. So in this example, if we select a darker clarity value for these lake systems, then we find these simulations produced by this physical model. Actually, here we use the general lake model, which is considered to be a state-of-the-art for lake temperature modeling. And these simulations produced by this model, we can find it's much lower than the true observed water temperature and in the middle layer of Lake Mendota. So this is because this clarity parameter actually controls how much solar radiation can penetrate downward the lake surface. And another limitation is that most of these existing approaches, they actually use physical simulations always in a separate training stage. They either use it to simply pre-train the machine learning model, or they can use it to augment the input drivers, but they never fully explore the relationships between these simulations and true observations. So in our proposed method, so we have two general objectives, and also this proposed method has such a two-stage training process. So in the first stage, we want to pre-train this machine learning model using multiple runs of simulation data that are produced under different physical parameters. And our objective here is to extract some general physical relationships that are encoded in these physical models. And the second stage is we trying to fine-tune this pre-trained model using the true observations. But at the same time, we also want to explore the similarity between these observations and simulations of different parameter settings. And also, we want to identify the variations of these physical parameters over space and over time. So this figure at the bottom summarizes the entire flow of this proposed method. So at the beginning, we are provided with the structure of these dynamical systems, or this spatial dependencies across different locations in the systems. And for each location, we are also provided with a time series of these input drivers over time. And then we have access to a physical model. And using this physical model, we can produce multiple runs of simulations using different physical parameters. And then by jointly learning from multiple runs of simulations, we can pre-train a customized machine learning model. And after we get a pre-trained model, we can further fine-tune it using observations through a contrastive learning process. So first, let's look at the pre-training phase. So the pre-training aims to extract some general physical knowledge from multiple runs of simulations. But before that, we want to first construct such a customized model architecture so that we can reflect how these physical parameters affect the model predictions. So ideally, we find most of these physical parameters, they actually determine how the system states react to some external input. So this means, like, if we consider there's a sequence of these evolving system states over time, so these physical parameters actually, they can be used to filter the information from these different external inputs. And then this filtered information can be used to update the system states. So based on this consideration, we built such a customized model architecture. So we call this as spatial temporal network, or STN. So in this model, we have two sets of model parameters. The first set of model parameters is called simulation specific parameters, theta. So this theta is different for different run of simulations. And this data is mostly used to create a set of gating variables in this architecture. So these gating variables are used to filter the information, for example, from the current climate drivers, or from the spatial neighborhood, and also from the past history. So they are mostly used as some filtering variables in this architecture. And the second set of variables is called simulation invariant model parameters, phi. And these model parameters are shared across different runs of simulations. And based on this architecture, our pre-training, the goal of pre-training is to estimate the initial values of these two sets of parameters. So this method is actually inspired by this ML, or this meta-learning algorithm in machine learning. So so the idea is that if we are given multiple runs of simulation data, and if we consider these multiple runs of simulation data are distributed in the space, and then our goal is actually to find a model in the middle of these multiple sets of simulations, so that this model can be quickly adjusted or adapted to each run of simulations. And to do this, we will first divide each set of simulation into two separate training and validation set. And then we will first use the training set to update the model parameters. And then we use the updated parameter data to calculate the loss on the validation set. So the final pre-training loss will be defined as a sum over all these different validation loss on all of these different set of simulations. And after we get the pre-trained model, we will further fine-tune this model using observations. So I will skip some details here, but the basic intuition is that if we consider some simulations are produced using more accurate parameters, using more accurate physical parameters, then there's a higher chance that these simulations is going to be more similar to true observations. And on the so in contrast, if some simulations are produced using less accurate parameters, then there's a higher chance that these simulations will be farther away from true observations. So there's such a contrast of similarity between observations and simulations. And that's why we build such a similarity mapping between true observations and each set of simulation one. And also we will use a contrastive loss for the fine-tuning phase. So this fine-tuning process can give us not only a final fine-tuned predictive model, but also as a byproduct, it is able to provide such a similarity mapping between observations and different sets of simulations. So we evaluate our proposed method in two different applications. The first one is to predict the water temperature in Lake Mendota. So Lake Mendota has a depth of 25 meters. So we will predict the water temperature in each depth layer of these lake systems. So we will train the model using data or using observations from this period, which has in total about 8,000 observations. So the observations here can be really sparse. That means these observations may be available only on certain depths layers or on certain dates. And then we will test the model in another period. And to generate simulations, we will use simulations generated under different geometry structure of these lake systems. So for example, we have tried using cone and barrel martini, these different shapes. And these three shapes actually have been very widely used in lake modeling community. And also we have tried generating the simulations using different values for clarity, water clarity in the lake systems. And the second application is to predict the water temperature in river network, Christina River Watershed, which is a subset of Delaware River Basin. So here in this river network, actually, the rivers are considered to be well mixed because they are shallower, but we need to make predictions simultaneously on all the river segments. So we will train the model using data from this period, which has in total about 34K observations, and then test in another period. And then we generate simulation data using different parameters, using the parameter of these, by varying these parameter values for this average groundwater residence time. So this parameter, this residence time actually determines how quickly this groundwater moves through the aquifer and enters the stream. So if we have a lower value for this residence time, then there's a higher chance that this groundwater temperature is going to be more similar to the recent air temperature. And we will look at the performance on several different aspects. The first one is we will check the performance of pre-training and fine-tuning, especially if we only provided the sparse data. And the second one is we want to see if we can get any interpretation of the learned similarity relationship between observations to different simulations. And the third one is we want to check whether these models can indeed generalizable to different scenarios. So first, let's look at the pre-training performance. So here we show the performance in predicting lake water temperature, and we show the simulations and predictions made for each different layers of this lake system, Lake Mendota. And the first column shows the learning performance using simulations generated with different geometric structures, cone, martini, and barrel. And the second column shows the learning using simulations produced using different clarity values, normal, darker, or clear. So we can see that on the lake, at the lake surface, most of these simulations or predictions, they can do a pretty good job in matching these true observations of water temperature. But in the middle layer and the bottom layer, we find the selection of these model parameters becomes much more important, because if we didn't carefully select this, like the geometric structure, we can see the simulations can either over-predict or under-predict the water temperature. And something we find is that the predictions made by our pre-trained model, this red curve, is always in the middle of these three sets of simulations. And remember that in our pre-training phase, we have no access to true observations. So that means the model has no idea of which of these three sets of simulations that they are more accurate to this lake system. But this pre-training is simply trying to generate or trying to extract some more general relationships or some patterns that are shared across these three sets of simulation data. And here we show the performance of fine-tuning. So after we fine-tune this, after we get the pre-trained model, we fine-tune it using 2% of observation. So remember, we have about like 8,000 observations in the training time. So we use 2% of data, that is about like 160 observations from the training period. And even just using this small number of observations, we can get much better performance in matching true observations. So we show this fine-tuned model using the green curve. And now we can see this green curve can match these observations much better. And even if we know that pre-trained model is not always perfect, but it is still able to extract some general physical relationship from these simulation data. And that's why we only need very few amount of training samples to close the gap between the red curve and the green curve. And this table simply shows that we also use a lot of different sparsity levels from 0% to 2% to 100% for this test. And in most cases, we find our proposed method give us better performance. And now we want to check what's the learned similarity from this contrastive fine-tuning process. So this figure shows the similarity between observations and different clarity values over different depths. And also this one shows the similarity between observations to different geometric structures over different months. So actually from here, actually these results give us some very useful information because we know that most existing lake temperature models actually they assume a single or static clarity value across all the depth layers. But from these results, it actually suggests that we may be able to select different clarity parameters for different depth layers. And this is actually consistent to our understanding of this natural environment. And this figure actually shows that these observations are more similar to the cone shape in the summer period, but it's closer to the barrel shape in the fall and winter time. And one hypothesis here is that this fall cooling period and this under ice temperature may be better simulated using the barrel shape because the barrel shape has a slower cooling process, which may be more appropriate for this lake system. And for lake temperature modeling, for river temperature modeling example, so we find most rivers in Christina River watershed are more similar to the simulations produced by this lower value of the residence groundwater residence time, and also they are more similar to this lower value in the spring period. So actually, this is consistent to our or some other previous study, which have shown that in this area, many of these shallower groundwater, so shallower groundwater usually have a lower value of groundwater residence time. So this shallower water usually contribute more in the springtime compared to other time periods. So finally, we also verify the generalizability of the model. So we train the model using data from, so this is for the lake temperature modeling. We train the model using data from colder seasons, spring, fall, and winter, and then we test the model in the summer period of the test period. So the second column here is more like a baseline where we still train the model using all the data from the training period. But the first column shows the performance of these generalization tests. So we expect an increase of prediction error from the second column to the first column. But we can see that our proposed method actually gives us a much smaller increase of prediction error in this case. So some of our future directions, so we will explore learning from a larger range of parameter values, and also we will try to learn from simultaneous variations of multiple parameters. For example, what if we vary the value of this geometric structure and also this clarity value at the same time? And also we have several ongoing projects which involve some similar methods. For example, we can not only identify the most suitable physical parameters, but also we can see if we can use similar approach to identify the physical models or some physical formulas that are more appropriate to use under different scenarios. So that's all about this talk today, and thanks for listening. Any questions?
Thank you so much, Xiaowei. So the first question in Slido is, Are observations also being used to bias correct the pre-training simulations so that they are closer to the truth to begin with?
Yeah, actually, I think that's actually a very good point. So let me just go back to here. Yeah. So I think there are several approaches for using this or combining the simulations and true observations. So so I think here we consider like doing this in this two-stage process, pre-training and fine-tuning. But like in some other domains like climate science, I've also seen like people have used the observations to first do a bias correction of these simulations, and actually that's helpful in multiple purposes, like especially for like reanalysis. So that would give us some good historical data. So I think that's a different view, but it's definitely relevant, and it's also a different example for how to find the relationship between observations and these simulations. Yeah, I think we will keep it. I think we will consider like comparing some of the baselines. For example, if we first do a bias correction of these simulations using observations and then do a pre-training or use it to guide the learning, that may give us better performance.
Okay. Next question is, what is the difference between the proposed network and graph neural networks?
Yeah, it's actually relevant. So this proposed method, it actually has this recurrent component and also a graph convolutional component. The graph convolutional component mostly used for capturing this spatial dependencies across different locations. So the major difference is that we consider, so there are lots of parameters in this architecture, and we divide these parameters into two different sets, theta and phi. So these data values, they're specific to each set of simulations. So that means the parameters used to calculate these scaling variables, they're different for different simulations. But some other parameters, like these parameters used for like output gating variables or some other fully connected layers, those parameters are shared across different simulations. So mostly, I would say this architecture itself it has its own like graph component, which is exactly the same with existing graph models. But we're trying to use these two different sets of parameters to reflect how these physical parameters play a role in this prediction process.
All right, there are two more questions, but we only have 1 minute left. So if I could get a quick answer on this question.
Sure.
There are many ways to fine tune. Is there a particular reason you favor your particular approach?
Yeah, that's a good question. I think the major I think that depends on the different applications, but I think here our major concern is some simulations are more accurate in this system, and some simulations are not very accurate. So that's why in our fine-tuning phase, we want to produce this byproduct of the similarity mapping, and that's why we use this contrastive learning process. But definitely, we in our experiment, we have compared to several different other fine-tuning process. And we have shown this method gives us better performance, at least in our applications.
Thank you so much.